Great, let's get started. Thanks
Okay.
for coming, everybody. Today we're pleased to have Andrew Jayich, who's joining us from University of California at Santa Barbara. Andrew did his undergraduate work at Harvard and a PhD at Yale in the group of Jack Harris. He then moved downstairs to do a postdoc with Jeff Kimball here in this building. Before moving to UCLA to a postdoc with Wes Campbell. Now, as faculty at UCSB, his group works on developing quantum technologies and doing fundamental physics measurements with trapped ions with an emphasis on quantum control. And his group has done a lot of work, in particular, as you'll hear about, with radioactive atoms and molecules. And in that area has done a number of very exciting firsts, including, but not limited to, precision spectroscopic measurements, making a radium ion optical clock, the first trapping and cooling and control of radioactive polyatomic molecular ions, and more. Andrew has received the NSF Career Award, the DOE Early Career Award, and a Gordon and Betty Moore Foundation Physics Innovation Award. Please join me in welcoming Andrew.
Thanks. Okay, thanks. Thanks for the introduction, Nick. Okay, so this is a view into one of our experiments, just to give some sense of what the lab looks like and what we do. This is a standard vacuum flange that's about 3 inches across, just to give you a sense of scale. And in the center of this apparatus, we have some electrodes that we use to generate fields to trap atoms and molecules with by acting on their charge degree of freedom. This picture was taken with a camera by one of my grad students. If we hold on one second. Okay. So if you zoom in on the picture, you can see that spread across multiple pixels is the light from a single trapped, in this case, radium ion. So this should give you a sense of like the degree of control we use and the scale of the experiments. So, you know, we work with single countable numbers of ions. So you can imagine we're going to have to repeat measurements a lot. And if we're...
Andrew, could you double check which screen you're sharing on the Zoom? It shows up as a blank screen.
Oh, okay. Okay. Sorry. Share screen.
You can also just try sharing the whole desktop one. It'll just share whatever you see.
Really? Okay. That might do the trick. Yeah. Okay. Hold on one second. Now I can't find my slides. Sorry. It's weird. Okay, hold on half a second. You can't, it's unbelievable that I'm an experimentalist, right? Okay.
And it was working before your talk. The tech demo work. Now try full screening it.
Okay. I think I've like cursed technology one too many times.
Yeah, this looks good.
All right, great. Okay, so everybody can see there's a single atom that was taken by with a camera by one of my grad students. So you get the impression that, you know, if you look inside here, you can see this single dot, maybe with your eye. Great. So that gives you some sense of the experiments we do. Here are just an overview of our experiments that we do with trapped atoms and molecules, ions. So I'd say our largest kind of effort and footprint is using radioactive molecules to kind of address outstanding problems in physics, or at least attempt to. We also have a definite interest in optical clocks, and synergistic to all this work is kind of developing like Nick said, new quantum technology. So developing kind of new ion traps for quantum computing that we can use for these other things as well. Okay, so what's the physics? So here's some timeline of the universe. We're way out here, and at this point in the universe, in time, the universe is just absolutely full of matter. At the early part of the universe, there was a point in time where there were equal parts matter and antimatter, and so kind of an outstanding question that we don't have an answer to is that how did we end up with this kind of asymmetry between matter and antimatter? We don't know what the physics is, but we know one of the key ingredients to end up with this imbalance is some time symmetry violating interactions that favored matter over antimatter. Okay, so how can we look for these things? A very nice way to look for them is to look for time symmetry violating moments of fundamental particles. So this is a good example. So you can think about this as an electron, and the electron has some spin associated with it in a magnetic moment. If you reverse time, this is all fine. If you imagine reversing time, the spin's going to reverse direction, and the pseudo vector is going to flip upside down. This is exactly what you expect to happen. Now, if in addition to a magnetic moment, if you add an electric dipole moment, so if you redistribute the charge of the electron to give it a little bit more positive on one side than on the other, you'll end up with a electric dipole moment. And you can imagine like a potter's wheel, if you reverse time and spin this electron backwards, that shape is not going to flip upside down. The dipole moment will stay pointed up. And this particle looks fundamentally different than this particle. This dipole, this permanent electric dipole moment can arise from some new particle interactions that could give us these time symmetry violating interactions in the early universe that gives us this matter abundance that we're surrounded with now. Okay, great. I should say I'm happy to answer questions as I go. So definitely just ask. Okay, great.
And to the remote people, if you on Zoom chat or raise your hand, I'll keep an eye on it.
Great. Okay, so an electron, we can also do the same search for this same kind of time symmetry violating moments of nuclei. Nuclei are more complex objects. So there's kind of quarks and gluons, et cetera, inside them. So it seems like a rich place to look for this type of physics. How do you do this? You put your nucleus inside a large electric field, and then you measure some energy level structure that's sensitive to this, to whether you have a dipole moment there, and then you reverse the electric field and look for a shift in your energy level structure. So this is like a simplified view, but you can imagine if you have a dipole moment, you flip it up or down in an electric field, you're going to see there's going to be some energy difference. Where's a good place to look for this type of physics? Well, these electric dipole moments are enhanced strongly with large nuclei, so very large Z. So kind of the bottom of the periodic table or thereabouts is promising. Of course, all these elements are radioactive, so you have to think a little bit, carefully about how to handle them, et cetera, et cetera. For us, one nice thing that you can do is you can look at laser coolable species, especially as ions, because you can use them really, really efficiently. So you can trap these kind of single particles and get pretty good statistical sensitivity. These are the common laser coolable ion species. You can see radium's right in line in this column. So we should be able to laser cool it and maybe apply it to these types of precision measurements. Okay. In addition to being heavy and laser coolable, radium comes with another feature. It has this misshapen octupole deformed nucleus. This is a rarity in the periodic table. Okay, and you can imagine this kind of shape. It looks kind of like you know, it might have some enhancement to time symmetry violations. Kind of misshapen nucleus. The real story is that this nucleus, the nuclear ground state consists of this octupole deformation up plus this octupole deformation down. Okay, that's what the ground state looks like. And it has an opposite parity nuclear excited state with octupole up minus octupole down. Okay, and what this deformation does, where the enhancement comes from, is the fact that some new T violating forces will mix these two opposite parity states in the laboratory frame and give you this octupole up shape, which gives you an enhancement to a time symmetry violating moment of the nucleus, a shift moment of the nucleus. It's 100 to 1,000 times bigger than Mercury, which is kind of the EDM touchstone, shift moment touchstone. So that's what's happening here. It's this small energy level splitting. Really, this is a big number, but this is a very small number on the nuclear energy level scale. So this is a perturbative term. That's a small term in your denominator. Okay, great. We can get a further enhancement, similar physics, by putting the radium atom inside a molecule, similar to the nucleus, to get a large electric field in the laboratory frame. You mix opposite parity molecular states, and this is something that Nick has pointed out and is an absolute expert in. So I learned this stuff from Nick. Okay, so you can get a further enhancement of a factor of 1,000 above an atomic system. These two enhancements are independent of each other, so you can put these, put together nuclear enhancement, put together the molecular enhancement, and get some overall enhancement to new physics that's fairly sizable for on a per particle comparison. What would this experiment look like? This is kind of what we imagine. We imagine trapping a single molecule together with a single atom and using them to search for this time symmetry violation. This type of experiment, or what we're envisioning doing, was really enabled by recent work, primarily at NIST, to read out the state of single molecules non-destructively with an off-resonant laser. So the basic idea behind this all comes from basically from quantum computing through optical clocks. Now this technique's being applied to molecules. Basic idea is that you shine light on your molecule. It undergoes a stimulated Raman transition. So this is far off resonance, so you don't care about detailed structure of molecular excited states. You're very agnostic to the wavelength. That will give the molecule a kick. So it'll give it a single phonon kick. And then you can read out and detect that single phonon kick with very high fidelity with the trapped atomic ion. So this is the quantum logic spectroscopy of molecules. So very efficient use of our molecule and the photons that hit it. Okay, where can we go? So with the single molecule, these are real actual measurements in the neutron EDM and in the mercury atom, and showing their sensitivity to one nuclear time symmetry violating parameter, this kind of quark chromo EDMs. This is kind of where we project to be with a week of measurement. This is a week of measurement with more aggressive coherence time, and looking towards some future, maybe we can switch the radium atom with something that has an even stronger octupole deformation. Okay, so okay, so there's hope that we can advance this. If I map these roughly onto energy scales of some new particle, this is roughly what you get. So if you want to compare this to you're sensitive to some 25 TeV type particle that gives rise to this new physics. I can phrase this in another way. So the physics that we're sensitive to, we're also sensitive to kind of an old problem in the standard model. If you're familiar with this, this is the strong CP problem. This is just the various experiment sensitivity to theta, and this is kind of where we project that we could go. Note that there's a range of experiments that are projected to get into this range down here in the next several years. So we're one group among many. This is good because unraveling and untangling the physics underlying these nuclear interactions is complex. So the more kind of measurements that are being made in different systems, the more we can kind of understand the physics here. Okay, great. Questions so far? Yeah. Oh, okay, sure, great, perfect question. Okay, so it's a little bit reduced, so there's other elements that work well. The key point is that on the far left of the periodic table, the alkali elements, they have a single valence electron. That single valence electron's bound with with enough energy that you can excite kind of the first excitations with visible laser light. And that's technologically very feasible. Their structure is also very simple, so you don't need a lot of lasers. So if you remove one valence electron to give a charged particle, you end up with something that's also laser coolable. Your transitions will be slightly bluer, but generally that's the starting point to search for something that you can laser cool, that column. Yeah, does that make sense? Yeah, okay, great. Okay, right. So with radium, before we started, not a lot was known, at least at the precision that an atomic physicist kind of requires. So there was roughly 5 gigahertz uncertainties in these transitions. These are kind of the core transitions for the ion. This is common to like strontium, calcium, other ions that are used for quantum information science. One note is that these transitions, especially this transition, is relatively very friendly. So this transition at 468 nanometers is pretty far from the blue compared to almost all other ions. And that's a pretty nice technological advantage. It's also radioactive. That's not a feature. Okay, so to start, to laser cool it and see that light that I showed you on the first slide, you need to address these 2 transitions. We didn't know them to, like I said, about 5 gigahertz uncertainty, which is a lot for laser cooling. Here's our setup where we did the diagram of our setup. These are our RF rods that are separated by several millimeters, which is huge compared to like trapped ion quantum computing, but ideal for kind of digging into the unknown where we don't know where these transitions are. Just showing kind of where the light is collected. And then there's a third laser coming through here. This is a pulse laser where we ablate a target of radium chloride to generate the ions that we laser cool. My students spent roughly a month, and then we saw this nice like radium ion show up on the computer screen. This is a picture of the second laser cooled radium ion on that first day. We're quickly able to make chains of the ions. This is kind of what you'd see for like some quantum computing paradigm where you use each of these single ions as a qubit and interact via their motional they interact with each other via their motional state. We had a lot of work to do. Like I said, not much was known. So a basic question you can ask is, when you're laser cooling this ion and the population goes up to this excited state, where does it decay? So what fraction of the time does it decay back down to the ground state? What fraction of the time does it decay back down to this metastable state? Those are that basic question underlies our understanding of transition dipole matrix elements to just do pretty super basic calculations that you take for granted with other, atomic species, and that are absolutely necessary for understanding systematic uncertainties with, like, for example, an optical clock. So you really need to know these types of values. So we can do that experiment. I'm showing you this data just to give you a sense of basically the time scale. So the time scale of this is in microseconds, and we repeat this experiment many times to build up these statistics. I think this was done, this data run that gave us this branching fraction was done in about an hour. Okay. It was nice that, our value is first measurement agreed with theoretical calculations. One small point is that radium's heavy, and so it's kind of a good test bed. Our measurements are a good test bed for atomic theory of kind of heavy structures. So theorists, these are good benchmarks for theory. Okay, right. Radium has this narrow clock transition at 728 nanometers. This is really important for doing qubit operations and doing the quantum logic spectroscopy of molecular ions that we'd like to do. It had never been driven before, so we had to find the transition, drive it, measure it, etc. Here's what I show this slide. This is what our ion looks like in the lab with some lens that really distorts the ion. And then these are the photon counts coming out of the ion. So we count the ion, the photons coming out of the ion on a PMT. And then we look at the ion simultaneously on a camera. And this is just one of my students in time, and this is space. And just as a function of time, my student is laser cooling the ion. It's giving a lot of photon counts. And then he's tuning this clock transition laser. And you can see the photon counts are dropping down when that clock transition is driven and the ion sits in this metastable state for several hundred milliseconds. So that's, you get a very clear signal of what the clock looks like, or what it looks like when you drive the clock transition. I enjoy this because this is, I don't know, this is what we get to see in the lab every day, these single ions on the screen. Okay, that's kind of playing around with the transition. We can dig in and measure the transition with respect to known lines in iodine to roughly tens of megahertz. I don't remember the uncertainty here, but it's limited by the uncertainty in the iodine transition. But that kind of measurement is definitely good enough for other atomic physicists to use this ion. Okay, right. So before 2019, this is kind of the state of knowledge of lifetimes and branching fractions, which give you transition dipole matrix elements of the kind of most important transitions. Okay, now we've kind of had a chance to flesh this out. Some measurements are ongoing, but this is basically pretty good for building like optical clocks on top of, etc. We did similar work measuring all these transition frequencies. Like I said before, this clock transition wasn't driven before, so we had a fair bit of spectroscopy to do. Each one of these papers has kind of a table of systematic uncertainties. So there's a lot. Okay, I'm just leaving a lot out on this, but these are fun measurements to make. Okay, great. So this is kind of you can kind of understand this whole structure and where all these various transitions are. Now, what we want to do is start using the ion, and in particular, start using this nice clock transition to this long-lived metastable state. So this upper state and this lower electronic state form a qubit in our system, and we can use this qubit for many things. So here's what Rabi flopping on this qubit state looks like. So this is coherently driving the population from the ground electronic state up to the excited state and back down, up, down, et cetera, and this is, this is only out to a millisecond. We have magnetic field sensitivity. So, this is what we can do with this particular isotope of radium. Okay, fine. So this is demonstrating optical control of this system. We can push that further. Instead of driving this carrier from the ground to excited state, we can park our laser detuned from the trap frequency, so the ion sitting in a trap, okay, and we can see those motional sidebands, so those are detuned by a couple hundred kilohertz, and we can park our laser on the red sideband and address this transition. When you address this transition, you add a phonon worth of energy. You take a phonon worth of energy out of the system in order to drive the transition to drive yourself to the excited state. So if you sit there, you can pull phonons out of the system and then do spectroscopy afterwards. And what you see here is a big asymmetry between these two sidebands. This sideband is proportional to the square root of the number of phonons, and this is proportional to n+1, square root of n+1 phonons. So this shows you that we cooled this ion down to its motional ground state, at least along one motional mode. This is important because we want to get rid of, we want to really control the phonon state so that we can do this quantum logic spectroscopy that I talked about. We want to get rid of all the phonons and have a clean bus for quantum logic. We can take this one step further. I should also note that all of this is done in a trap that was not designed for this work. So these are very low. This is very low frequencies for doing this kind of sideband cooling. Typically with like calcium ions, this is 2 megahertz or something like this. So we kind of had to work a little bit to demonstrate this, but okay, that's fine. We're just pushing a trap right now. Okay, so fine. So you can, after you cool to the ground state, you can address this transition. When you address this blue transition, you are controllably adding a single phonon worth of energy to your system. So you can see that here, where now we're Rabi flopping on this blue sideband and controllably coherently adding one phonon. So this is creating a phonon Fock state in our system, and this is getting to be a pretty good starting point for working with molecules. Okay. In a separate but related vein, we drove the carrier transition, and by controllably probing that transition, we can back out its center frequency. And with this, we made an optical clock with radium. You might think this is crazy to make an optical clock out of a radioactive element. Well, why would we do this? Okay. Because it has these good wavelengths that in the future, maybe we could make a clock with some integrated photonics on the chip and have some transportable optical clock. We've given this some thought, and we think that we can make a clock so typically you need 4 lasers to operate one of these clocks. We think we can reduce it down to 3 lasers with a particular isotope of radium. So radium has a big nucleus. A big nucleus results in large hyperfine structure, and with large hyperfine structure, your states are pretty well separated. So you can use kind of state detection and control paradigms that rely on this hyperfine structure splitting that you can take advantage of. We think that we can even get rid of this 468 nanometer laser and make an optical clock with just 2 lasers that are pretty convenient to work with integrated photonics. Okay, fine. This may be a little bit of a digression. Okay, but what do we really want? We really want, okay, this is what I really like to do. Okay, clocks are fun, but we really want to do kind of address a lot of this fundamental physics with molecules. So making molecules in an ion trap, if you have radium ions, it turns out that with a little bit of pre-planning, making the molecular ions is pretty easy, kind of. You can leak in a reagent gas. In this case, we leaked in some methanol. And if you wait and you kind of tune your pressure just right of the reagent gas, and you're a little bit patient, a dark ion will show up. That dark ion is a molecule. That molecule is trapped. We don't, in an ion trap, you don't use, light is not used for the trap at all. So it's just the monopole of charge. And because we have these laser cooled radium ions sitting next to it, that molecule is cold and fixed in position right there. So this is good. I'm showing this slide with 4 ions, 3 radium ions, just to make it clear where the molecule is. So, okay, so in a real experiment, you would just see one bright dot and you wouldn't see the molecule at all. Okay, how do we know? So the next question is, how do you know it's this particular molecule? And we did not have a good answer to that question. So we didn't even set out to make this molecule until we actually kind of figured out how we would answer this question about what this molecule's identity is. So how do we do that? Okay, this is what a trapped ion looks like. Single trapped radium ion. My student Mingyu Fan was playing around one day with the lasers, and he saw this radium ion kind of transition between this nice laser cooled guy to this smeared out line. Okay, and he said, "Oh, okay, what's this?" And I said, "I don't know. Why don't you just play with it for a week and just see what you can come up with. This looks kind of fun and interesting." So Mingyu dug into this and thought about it and took more data and played with this system. And here's what he figured out. So this is the what I'm showing you is the probability of exciting the radium ion to this P1/2 state, this kind of this laser cooled state right here, this state used for laser cooling, as a function of its detuning. Okay, and then we detuned this 1079 nanometer laser, the second laser, to some point here relative to its transition center. And what you end up with here is interference between these two lasers that generates this dip, okay, in the spectrum. Ordinarily, when we laser cool, this 1079 nanometer laser is parked over here. It doesn't actually do much laser cooling actually at all. It actually heats the ion a little bit. And there's no kind of interference that shows up over here. So laser cooling happens on these positive slopes here, okay? And on this negative slope, what you actually end up getting is coherent amplification of the motion, okay? And so you can, if you park your laser here, you'll see this coherent amplification. It'll get amplified up until the point where it starts to come back over here or starts to go up on this side, and it starts to get laser cooled again. So it's coherently amplified, but it hits limits on either side here. Okay, great. Yeah.
You park on the blue side as well, like that large slope on the right.
If you do that, what you'll end up doing is I think you'll basically heat your ion into some really big orbit, because it's not going to be bounded by kind of laser cooling on either side. So like as the orbit increases here, it will stop because it gets laser cooled. But over here, it can kick off into some.
It's like more control heating, like heating up the point.
Yeah, or amplification up until a point. Yeah, exactly. Great. So what's special about this? Okay, the ion's moving, it's coherently amplifying its motion in the trap. Okay, so it's a harmonic oscillator, right? It's a trap particle, it's a harmonic oscillator. So you can take the Fourier transform of the trapped ion, right, and get some frequency associated with that, and back out its mass by root k over m. Okay, we know in this case that it's a radium ion, so we can just say, hey, look, its mass is 226 Daltons or whatever it ends up being. Great. I'll just say that to take this data set took like, I don't know, 2 or 3 seconds. Okay, and what I'm not showing you is like how broad this data set is. Okay, so it's like super broadband. So, you know, a priori, if we didn't know the mass of the radium ion, we would see this peak show up super sharply. Okay, and it's non-destructive. So great. So we have some mass dependent measurement capabilities, or some ability to measure mass. So we can put in our reagent gas, react them with one radium ion, have another radium ion in the trap, and then do this measurement. Okay, and so we can see these kind of exotic molecules show up, RaOH plus, RaOCH3 plus out at these points. How do we, you know, what can we do to confirm that? We can put in deuterated methanol, and we can see their isotopologues show up at, you know, 1 Dalton or 3 Daltons away in this case. So it's very high precision, non-destructive means to measure these molecular ions, and really good for small numbers of molecules. We use this a lot in our lab. Anytime we work with molecules, this is kind of our starting point. Okay, great. Okay, great. Okay, so I should point out, like, why are we looking at these crazy things? It's because I came and visited Nick, and Nick said, hey, look, these are actually really interesting molecules for precision measurement. I knew about this one from Nick's earlier paper, and Nick had been thinking about symmetric tops. For our precision measurement purposes, we'd been seriously considering this molecule, RaOH plus. The one issue is the excited state lifetime is about a second. So we said, oh, Nick, how do we get around this? And Nick and his grad student Phelan have, you know, great molecular intuition and been thinking a lot about molecules. So that, you know, what we can do is make this molecule RaSH plus, which just turns out that it has its science states and its ground states. This just a weird bent molecule. They told us about this, and like basically about a month later, we were making hydrogen sulfide in very small quantities in the lab, leaked it into our system, and then okay, and then we can see this you know, this molecule, this dark thing show up, and then do this mass spectrometry and identify the molecule. Okay, so that's fun. Okay, great. Okay, haha. Okay, so so all the work I've been talking to you about has been done with radium-226, which is a spin 0 nuclear isotope. If you remember a slide on like how we're going to measure time symmetry violation, there was a magnetic moment there. You need that magnetic moment to give yourself some orientation with which to actually see, you know, time symmetry violation between magnetic and electric dipole moment. A nucleus, like this was radium-226. The way nucleuses are built up is they're built up in pairs of neutrons like this, for example, and in pairs of protons like this. So those form the nuclear shells, like your electron orbitals in your atom. And those shells, when those two nucleons pair up, you get net 0 nuclear spin, and those orbitals, like in your atoms, give you something that's more stable. So like, you know, helium, the noble gases have the electronic structure that's very tightly bound, very stable. The same is true here when you bind up nucleons, you end up with something that is generically more stable and does not have nuclear spin. So if you want to have nuclear spin, you need to add in a valence nucleon where, you know, itself can have spin and it can have some nuclear orbital angular momentum to get magnetic moment. Okay, great. If you add in this nucleon, you're going to drop the stability, right? Okay, so the universe is full of hydrogen. So if we exclude hydrogen and deuterium, there's a lot of, if you consider other elements, a lot of the stable isotopes are nuclear spin 0 for this pairing reason there. Okay, so we want spin. So what does this look like in radium? So in radium, this is 226. We just work with a solid sample of this element or this isotope with a 1600-year half-life. We want to work with radium 225. That has nuclear spin 1/2. That has what we want. It also has a half-life of like 2 weeks, right? So that's problematic. Fortunately, there's a way to produce this element from its parent isotope in enough abundance that we can do our ion trapping work. So the way this works is that thorium, this thorium parent, 229, decays to radium. You can heat up this oven and inject out your radium 225 that has a vapor pressure that's trillions of times lower than thorium. Thorium's very refractory, so you should be able to just, you know, keep this mother isotope inside the oven, effuse out radium atoms, and then photoionize them, and your ion trap and work with them for 14 days. Okay, we know this works. A group in the Netherlands made such an oven to do spectroscopy of the neutral radium atom. We have been working pretty hard to get such an oven working, going from some, you know, me trying to reduce this down to some very, very simple ovens. So this is what we use for all our ovens now. We make 3D printed ovens where we just load in strontium into them, for example, and load our traps, to us kind of getting increasingly complex design, to chatting with another atomic physicist, Dave DeMille, who said, hey, look, ovens are a solved problem by the molecular beam epitaxy community. So we are in the process of testing and working with such. We are doing all our testing right now with, it turns out that thorium 228 is kind of a waste product. So we're doing all our testing of this oven with radium 224. Radium 225 and thorium 229 are a little more expensive. We have some reserve supply of them that we'll use once we get this worked out. This is, radioactive stuff wasn't too hard until we, you know, started having to think carefully about chemistry and things like this, but this should work soon. Okay, other ingredients. We've been working on a trap upgrade. So I showed you measurements done in a massive trap, not something that's good for quantum information science or quantum logic. We've since got a trap from, or made a trap that's kind of identical to this super high precision trapped ion optical clock based on the aluminum ion and aluminum quantum logic. So this is a diamond wafer that's been gold coated. I guess you guys probably heard a talk on diamond last week. So we have some diamond in our lab that holds this trap. This is all obviously not in vacuum. We recently trapped ions in this system and should start probing molecules and start doing this quantum logic hopefully soon in the next couple months. This system's baking right now. So once it's done baking, then we can start really making molecules and trying to do this. For the experiment that with these polyatomic molecules, we really need to work in a cryogenic environment so that black body radiation doesn't drive transitions and that you start in a limited number of states for this quantum logic spectroscopy. In a separate effort, we have we built up a cryogenic system. This is we purchased kind of the cold plate, but everything above that was designed by one undergraduate in my group, which which is amazing because it worked. I was as nervous. This is a chip trap from Lincoln Labs. So Lincoln Labs wants other people to use their traps, and we wanted something simple to start vetting this system. It's pretty complex. There's a lot of electrodes, a lot of there's a very I guess I would say advanced resonator for generating our trapping voltages here that this undergrad really yeah, this is a real tour de force. This is what the system looks like on our optics table. This is very similar. You can't even tell it's a cryogenic system. It looks like all our other systems. It just has several fiber ports and lenses directing light into the ion trap in the center. We're doing this for another effort where we want to quickly cycle vacuum. So the very nice thing about this system is we can change traps in about 12 hours. So it's in a room temperature system, the equivalent operation would take 2 months and is basically a non-starter. Just showing you that, you know, the system works. We're measuring heating rates by cooling our system down into its quantum ground state, and then just waiting and watching it heat up. So you can see this red sideband start to grow as phonons start entering into the system. Okay, great. So this is an important ingredient that we now understand for kind of doing advanced work with polyatomic molecules. Okay, that's roughly where we're at. Here are all the people who've done this work. I'll just want to highlight Mingyu and Craig, who really took most of the, almost all of the radium data was and work was done by these two. We have a new postdoc and new graduate students in the lab, and this is I should get Chao Shen's picture on here. He's the guy who did this cryogenic ion trapping work. Okay. Thanks for your attention, and I'm happy to answer questions.
And as a reminder for our Zoom participants, you can raise your hand or put something in the chat window if you'd like to ask a question, and then you can mute yourself or type it, but we can also take questions from the in-person audience.
Uh-oh. Yeah, no. No, sorry. Okay, great. I think I went too fast. Like if there's technology snafus and I start to speed up and okay. So how does this work? We have our for quantum logic spectroscopy. You have the logic ion, which is your atom, which you can control super well. You have the molecule, which is your spectroscopy ion. That's quantum, and that's that's not quantum. This is logic, and that's spectroscopy. What you do for quantum logic spectroscopy is you cool your atomic ion to the ground state. It shares, and when you're doing that, those two, the molecule and atom, are super tightly bound together. They're oscillating like this. They've totally shared motional states. And so when you cool the atomic ion down to its ground state, whatever that mode is, the molecular ion is also in that ground state. So cool it to the ground state, shine light at the molecular ion. If you excite a transition, if you successfully excite a transition, there will be, and you're driving the blue sideband of the molecule. So you're driving the, hold half a second. So you're driving this blue sideband of the molecule for the molecular transition. So that will excite, if it's on resonance, it will excite one motional quanta. Then with the atomic ion, you can read out that single motional quanta. So the key, what's the key point? The key point is you can take that one excitation and turn it into thousands of cycled atomic phonons, because you can shelve the atom and make it dark or bright, depending on if the molecule is excited. Yeah. This is the just to be totally clear, this is not my idea. This is the basis of the aluminum ion optical clock, and NIST has really run away with this with molecular ions in the last 5 years, basically. The last 5 years, they've had a lot of really nice publications with calcium hydride. And I like this. One of the real appealing things to this is that these lasers, like, this is some molecular excited state. You don't know what it is, where it is. So you can switch the molecule and that state will move around or whatever, but you still have off resonant lasers that can drive stimulated Raman transitions. So in calcium hydride, they're 300 terahertz away or 200 or something. So it gives us some flexibility to change molecules. So yeah, maybe that's what, yeah. It's fun. Yeah.
So you showed your cryogenic apparatus.
Yeah. Yeah.
You wanted to do like a spin precession measurement, you have to worry about straight fields. What your plan for building up the EDM science.
Yeah, great, perfect. Okay, so there's a couple points to make here. One of the points is that we have this atomic ion that's kind of on board for the ride. I'm showing you just we unshielded. So our optical clock was an unshielded optical clock. The coherence time was not very long, et cetera, et cetera. And what I'm showing you is the corresponding magnetometry data that comes from that atomic ion. So that's point one. We have this atomic ion there that we can use to do like magnetometry. That's one point. A second point is that in the cryogenic environment, this is well demonstrated actually by the people at Lincoln Labs. You can put some superconducting rings around your trap and they will exclude magnetic field and really reduce noise. So yeah, I'm maybe overly confident that we have a lot of handles on a very small system that we should be able to understand pretty well and understand stray fields and stuff like this. And we haven't even gotten outside of the system with considering shielding or active feedback. I've thought a lot about active feedback.
And this magnetometry you're just looking at as the line limits for the magnetic field you're scattering region.
Correct. So the ground state of radium 226 is a m sub f equals +1/2 and m sub f equals -1/2. So any magnetic field drift will make those move, and we're sensitive to that with the clock. Yeah. So it's for a clock, we don't want it to be a nice magnetometer, but it is. With radium 225, that won't be the case because it has magnetic field insensitive states for a clock. It also has magnetic field sensitive states, so we could use for this kind of. Yeah.
You showed some projected sensitivity estimates for
Sure.
both the QCD and the EDM,
Yeah.
which look very impressive.
Okay.
Are we talking about miracles, or is there a clear path to getting there?
Okay. Sure. So this is one molecule, 1 second coherence time, and a week of measurement. Not easy. This is 1,000 seconds of coherence time in 1 week. We think we can do that. As a point of reference, magnetic field sensitive ytterbium, sorry, not magnetic field sensitive. So ytterbium ion demonstrated like a 1 hour coherence time with some, careful pulse sequences and stuff. We think we can push this down. This protactinium, so this relies on switching the nucleus from radium to protactinium. And the essence behind maybe how you can get this sensitivity is the fact that this energy level splitting is posited to be 1,000 times smaller, so 50 EV splitting. That needs to be measured. That's a key thing that needs to be measured that, I don't know, nuclear physicists are trying to measure. I'm in a small collaboration trying to measure that. We, in our lab, we're spending a lot of time trying to think about the ion trap that we'll use to polarize the molecule. I'd say that's the hardest thing here. I sure hope we can do these measurements and figure out the various problems at the outset. Like, okay, it feels like it's getting harder and harder, but like, okay, fine. I think a lot of that is that, the atomic atom we want to use is hard to generate. And I think we're going to break through that soon. Like every test we've done has had a distinct failure. It's like, okay, well, that was not right, but the turnaround time is just slow because we're dealing with Oak Ridge to get material and stuff like this. For the EDM stuff, yeah, I don't know. I think it's reasonable. It's not super crazy. The thing you really start to worry about is systematics for these, when are the systematics going to come? And I just want to emphasize, like, we're working with these single ions that can achieve these like pretty high systematic on pretty low systematic uncertainties. I don't know. We'll see. I hope somebody somebody gets down there.
Friendly competition.
Yeah. Much friendly competition. Yeah. Friendly kibitzing. Yeah. So I don't know. I'm optimistic. It's hard. Yeah. Cool.
Yeah. Oh.
Yeah, okay. So it's a okay, so yeah, fine. So it's okay, it's a combination of the molecular enhancement that's just calculated. So there's good chemists who can calculate this. Anastasia Borshevsky's an example. That molecular enhancement for a heavy molecule, heavy atom, it's kind of it doesn't vary much. Okay. The nuclear enhancement is this radium nucleus, and that's again relies on kind of like nuclear physics calculations. It's hard to get a lot of like ear time or like to get people to like try and refine this more, because it's a chicken and egg problem where they're like, yeah, we know it's going to be pretty good, like, but I think they're like a lot of nuclear structure theorists are spending time on neutrinoless double beta decay calculations or things like this. Okay, so they want to see a non-zero measurement, and then they'll just start going crazy. So those two enhancement factors, and then where is this plot? Right, and then from there we just we can back out a frequency sensitivity as a function of time, and then map that onto this kind of quark chromo EDM sensitivity. These values are all very rough, and then talk to theory friends to get a rough phenomenological new particle mass. Yeah, or kind of similar thinking to get a theta QCD. No, it's just statistical, fully statistical. These are measurements, right? This is the real deal. Everything in black here or in dark is filled out is real. This is statistical. And yeah, so right. Yeah. So okay, so one very nice. Yeah. Yeah. Oh, for sure. Wait, you sound like someone who works with a lot of cesium atoms. So no, so I think that so credit to Yan Zhu, who's at UNLV. You can imagine like a very simple extension is to just use two molecules and two atomic ions, and then do a measurement where one's in a state that has an opposite EDM sensitivity at the same time. And then you're going to get statistics at whatever it is, √2 times faster, but your sensitivity to like systematics then is going up dramatically, right? Because you're going to make measurements of states that, you know, have opposite, you know, magnetic field sensitivity or whatever, to get rid of systematics. So that I'm just saying that's a simple first order extension. And then you can imagine for sure going to more. Yeah. Yeah. I mean, yeah. No, I think this is the right direction. I just,
I think it's a little different from maybe one of them small, and everything has been back, but you don't have stuff in back. One molecule, one beat out,
yeah,
and if you calculate 100 times,
probably
10 times more.
yeah.
One out of making it.
No, absolutely. And you can see, like I said, the coherence.
50,000 on a chip, you know, and they all have to interact and you shuffle it around.
Yes. Yeah, no, I think a lot of the things that they're trying to do are much harder. I'd say that one of the hardest things for us is polarizing the molecule. So you know, there's definitely difficulties here. Yeah, no.
Each part is easier.
No. Yeah. If we, yeah, each. Yes.
So I'm just saying, you really want it to pay 100 million. Go light out of like go light out of 1,000 iron traps.
Yeah.
Maybe we should.
This is the right. This is good. Like, yes, this is the right inspiration. Yeah.
So if you have more than one ion, you entangle them.
Yes. Yeah, sure. So yeah, so the alternative is like you can use 10 ions and like do some, you know, some entanglement protocol and make a super spin of the 10 ions. I haven't thought in super detail on that. I mean, I know for clocks that you don't win with a fully entangled state because the fully entangled state like decoheres 10 times faster or whatever. So yes. Yeah, gosh, okay, yeah, okay, right, I should think about this more, but yeah.
Why
Sure.
don't we all
Yeah,
thank
okay.
Andrew again?
Okay, thanks.